Alright, so this will be our first homework video for AEM 535, Applied Finite Element Analysis. And if you saw the video I had made previously on creating a Schedule 80 pipe in HyperMesh, I'm going to redo that in this case because I want to make sure that I have enough nodes, few enough nodes, so that you can use this mesh with the student edition of ABAQUS. Student edition of ABAQUS supports 1,000 nodes. The teaching edition supports 20,000. If at all possible, please install the teaching edition of ABAQUS that I've given you access to, because we do want to do some things that will require more than 1,000 nodes. For some reason it just doesn't work for you, let me know and we'll work with it. But please try to get access to the teaching edition. So just as a review, I picked a pipe out of a pipe chart. It's 24-inch outside diameter, Schedule 80 pipe, has a wall thickness of 1.125 inches. And we're going to model just a section of it. We're going to model about 36 inches long. And we are going to use the inches and pounds system. And if no other reason, we're gonna see that this is kind of hard in English units to do heat transfer, and we'll gain I think an appreciation for the SI system. Okay, so we're going to have a section of pipe along the length. So the side view of it, and we want that section of pipe to be 36 inches long. And what we're going to do is we're going to apply a uniform stress to this pipe and tension. Of 100 psi. Let's make it a little more interesting. Let's do 1,000 psi. That'll be 1 ksi. And on this end, we're going to fix it. And we're going to fix it. We're going to over-constrain it initially, and I want to show you what happens when you over-constrain things. And then we're going to try to do some things to get the constraints so that we have a nice uniform stress distribution. We're going to do a couple things. I want us to determine the displacement of the pipe, at the end, so the change in length of the pipe, and then we can also use that to calculate the axial strain. So let me bring up my HyperMesh model, and I've gone ahead and created the mesh in a similar way that I've done before. And but what I need to make sure that I have gotten rid of any seams, any duplicate nodes. So I'm going to go in here and go to Tools, and let's check our faces. Here's the component that we're going to check, and we're going to preview the equivalence. And you can see when I do this wireframe, it has selected these nodes, so we want to get rid of those duplicate nodes. If we do not get rid of those duplicate nodes, it's almost like you have maybe a sheet of paper that's curled up but not connected. It's not the kind of structure that we want, so we need to make this get rid of these duplicate nodes. So I'm going to hit equivalence. Alright, so if we find our faces now, we shouldn't have any gaps or edges, and that looks fine. I'm going to turn off the faces so we can just see our pipe. And I want to make sure that I have few enough nodes that the student edition will work for this analysis. I do want you to try to get the teaching edition to work, but for now, if you have the student edition, we'll work with it. So I'm going to go here to Tool and count elements that are displayed, and let's see what we have. We have 972 nodes in here. So that's less than 1,000, so we should be okay to use this even for the student edition. Now what I'm going to do is I'm going to give you this mesh. We're going to worry about mesh creation a little bit later. There are some things you want to be careful about when you create finite element meshes. But for now, this is going to be okay. But I do want to point out that even now we have kind of an approximate version of what our pipe really looks like. If I were to show you these lines for the ID and the OD, let's kind of zoom in on it. We're using what are called first order solid brick elements. And they don't really match the curvature of our circle completely. See how it's kind of a straight line in between here and here. Now, if we used higher order elements, and we'll talk about those in class later, then we can probably go ahead and match that curvature a little bit better. Or if we wanted to use maybe twice as many elements, that cutoff of the curvature wouldn't look so severe. So by discretizing our structure, we're already introducing potentially some geometric approximation to what we really have. All right. So let me turn these lines off. And what I'm going to do is go here to File and Export a solver deck. It'll be ABAQUS, and I'm going to change this to without seam. Now when I first did this, I forgot again, which happens, is I left the seam in there and it had a gap. Maybe I'll try to show you what that looks like if we don't correct for that seam. But I'm going to output what's displayed. I'm going to hit Export, and it has just created that. So I think we're done with this. Let me save this under another name. Sometimes I like to put the date in here. And I'll minimize this. Now, next let's start up ABAQUS CAE. And if you're on Windows 7, you go through the Start menu, and you need to find the folder that says Dassault Systems Simulia ABAQUS CAE, and in there start up ABAQUS CAE. Now remember, in order to access the teaching edition for our university, you need to be on our VPN. It says 19 out of 20 licenses are available. If there are a lot of people using this, you might have to wait till somebody else is done. But this, the analyses that we're going to do usually should be short enough that you shouldn't have to wait long. Right. So it comes up with this window. We're just going to X out of this one, and I'll bring this over here. I have two screens, so it showed up on my other screen. Now it comes in here with a blank model, and this is the part that you're going to do. I'm going to give you this mesh that you're going to import, but I'm going to go File, Import, Model, and here it comes up with CAE, but I'm going to change this to INP file, and I need to find where that is. So I have it in here, and it's the pipe without the seam. Alright, and it's brought this in here. And if we go to this Rotate View button, and I'm left clicking and holding, we can rotate this section of pipe around. Alright, so we can see there's a coordinate system down here. It's matching our coordinate system that we have, X, Y, and Z. The origin of our coordinate system is down on this left end. Alright, so this is where 0, 0, 0 is in our model. Alright. So what we're going to do is we need to kind of go through, and all we've imported are the nodes and the elements. Now I want to give you this mesh so you don't spend your time trying to create the mesh in this case. There's a few things we need to do. If you go to this drop down, it says assembly right now, but we need to start with property, and we're going to put in our properties for our material. So I'm going to change the name of this to steel. We can put in a description if we want. And we're just going to do a linear elastic stress analysis. So I'm going to go down to mechanical and elasticity. If I can get that arrowed over. and it's going to come up with this window. So it's elastic material behavior. We're going to use an isotropic material. That means it behaves the same in all different directions, and we need to put in our Young's modulus, or you may call it here called the elastic modulus of the material, and our Poisson's ratio. If we had temperature dependent data, then we would check this box and we would put in temperatures and different values of the modulus of elasticity and Poisson's ratio at those different temperatures. Let's review what these terms mean in case it's been a little while since you've seen these things. I'm going to try to draw a set of axes for a stress-strain curve. And you may remember from a previous class that if we have a linear elastic material, the stress-strain curve is a nice straight line, and the slope of this line, as long as we're below the proportional limit, is the modulus of elasticity. All right, so E is delta sigma over delta epsilon, as long as our values for sigma are less than the proportional limit stress of the material. Now, we've created this model in inches. So our length unit is inches, and we're going to put pounds per square inch on it. So our force unit is going to be pounds, and our stress unit then will be pounds per square inch. So when I put in my number for my stress, if I put in 1, and I'm thinking, well, I got 1 KSI on it, well, really what that would be applying to it would be only 1 pound per square inch. If we want 1,000 pounds per square inch, we need to put in 1,000 into our load dialog box that we'll see in a minute. All right, so let's bring this back. Now that also means that my units for modulus of elasticity has the same units as stress. So I need to put in my modulus of elasticity with a value that has pounds per square inch. Now if we go with steel, that has a modulus of elasticity of about 30 million pounds per square inch. So we're going to have to put in the unit of 30 million. Now our Poisson's ratio for our steel that we're going to use, we're going to assume that the Poisson's ratio value is 0.3. Now you may remember that Poisson's ratio is defined as I'll write it over here, is the ratio of the diametral to the axial strain in a tension test. So if this is the axial strain direction and this is the diametral strain direction, if we pull on that in tension, Poisson's ratio is defined as minus the diametral over the axial strain. All right, so let's get back to our dialog boxes. So here, we don't put in 30, we don't put in 30,000, we need to put in 30 million pounds per square inch and Poisson's ratio of 0.3. Now we will work other problems in the Newton and millimeter system, which in the long run will probably be more comfortable for you, but there are occasions where you want to use English units. Alright, so we have that in here. I'm going to hit OK. So we've created a material. Next thing we need to do is create a section. I'm going to hit this box. We have solid elements, so that's why this is selected here. It's homogeneous. You could have composites or something like that, and that's fine. So we're going to hit continue. We're going to select our material, which we just defined as steel. We can create a new material, or we can select a different one here if we want. But we're going to hit OK, and we've created that section. Now the next thing we need to do is to assign the section. So I'm going to go to this box. Now here it says select the regions to be assigned a section, and it may say as default individually, or it may say something else. Let's select individually. What I'm going to do is I'm going to drag a box around this. I have my cursor. I'm going to take my mouse. I'm going to left click and hold. See how it's dragging that box? I'm going to select everything right here, and then I'm going to release. And all of that changed color. I'm going to hit done. Now the section that it's going to be defined is going to be what we call section 1. If there are complicated problems, you may have multiple sections, and you can use this drop down to pick the right section to call it. And this is fine, and then we're going to hit OK. Now notice it changed color. That means that we've assigned our section. So I'm going to expand this so we can see what's going on. These other things are for composite materials and we don't need them. We're going to kind of keep going down this list. An assembly is if you have multiple, what they call instances of this part. So you might have 10 sections of pipe that look just like this, and you want to say, I only have one model that I want to create, and I want to put it in my assembly 10 times. Well, we're just going to do this one piece, so we don't need to worry about the assembly. We're going to go down to step. See, it kind of goes in order. Now right now we have a step called initial. We're going to put our boundary conditions in the initial step, but we're going to make a step that has the loads in it. So we're going to create a step. You could call it step 1. It's going to be right after initial. It's going to be a general procedure and a static general type stress analysis. We will look at some of these others a little bit later. So we're going to hit continue. And here it has a description we can put in a time period. Now the fact that we've chosen our force unit to be pounds and our length unit to be inches, we are automatically now having seconds as our time period. Okay? So what this time period means then is this analysis will take place in 1 second. If we have a linear elastic material like we're assuming that we have, then the time really doesn't matter. It's not going to affect the stresses. However, if you have something called a viscoelastic or viscoplastic material, something where the material behavior changes as time continues on and changes, then the time is something you want to pay much more attention to. For our purposes now, this is fine. Nonlinear geometry, we'll just leave that off, and everything else we'll take as defaults. We'll have a maximum number of increments of 100, and we'll leave all these other defaults here. Now we do need to keep in mind that maximum number of increments when I show you how to make multiple calculations along our way to 1 second. But this is okay. So now we've created steps. The next thing we'll go to interactions is if 2 parts touch each other and need contact. Next thing we'll go to is loads, and it's loads and boundary conditions. Let's go to initial. Let's create a boundary condition. We can select this selection here, create boundary conditions, or we can go into the initial step, left click, and then right click and create a boundary condition. Now we're going to do a mechanical boundary condition, and there are different mechanical boundary conditions we can apply based on velocity or different things, acceleration. I don't usually like to use this in cast condition, and we'll show you why in a little bit. But right now what we're going to do is we're going to select displacement and hit continue. Now here it says select the regions for the boundary condition, and right now it's saying individually. So I can go through here and I can select individual nodes to apply displacements to. But really what I want to do is I want to select this entire bottom edge. So I'm going to change this drop down to by angle. I'm going to highlight this. See, it changed, highlighted all those, and then I'm going to select that edge. Now if you select a different region, it'll highlight different edges of the model. But I want this bottom edge, so I'm going to left click on it. It's going to turn that from orange to red, meaning it's been selected, and then I'm going to hit done. It's going to pop up this dialog box. Something that we'll talk about a little bit later in class is that solid elements do not have any rotations associated with their nodes. So what we're going to do is specify that the displacement in the 1, 2, and 3 directions are 0. It's in the global coordinate system right now, and this is our global coordinate system. Now 1, 2, and 3, what that means is the x, the y, and the z directions. Okay, so X is 1, Y is 2, and Z is 3. So, you might think of this as U, X, U, Y, and U, Z. I'm going to hit OK. And it puts these symbols on here indicating a fixed condition. Let's zoom in on this a little bit. They actually stay the same size, but each of these nodes then have, it's kind of hard to tell, but there's like 3 little arrowheads, 3 little symbols indicating that the displacement is fixed at that node. If you only fix 2 directions, then it would show 2 arrowheads. So you can kind of look at it and see what's been fixed. All right, so the next thing we want to do is we want to go into step 1, and we're going to create a load. So I'm going to select that. I'm going to right click and create a pressure. And now it wants to know what surface we're going to put the pressure on. We put it on the outside surface. We can put it on the inside surface, like you might have for a pipe. But for our practice, I'm going to rotate this around, and I'm going to select the other edge. Now when I rotate, it's still kind of in rotate mode until you hit this X. And by angle is selected. I'm going to highlight this edge, change its color, and I'm going to select done. And it's a uniform distribution, and I'm going to put a magnitude. Now pressures are stresses that push into a surface. I want this in tension. There's really no reason why it needs to be in tension, but I just like doing things in tension. So I'm going to put in my 1 KSI, or my 1,000 pounds per square inch. Again, we need to have a consistent unit system. Here it says the amplitude. The amplitude is specified as a ramp. That means from 0 seconds to 1 second, it'll be kind of a straight line increase of load with time. If we wanted to, we could specify, as part of a sine wave or what have you, by telling it exactly what time and what load needed to be. This is fine for our purposes, though. We'll select the default and hit OK. And so we see these arrowheads coming out of these elements on this side. Alright, so I think we're pretty close. Let's do something else. Let's see. One of the things that I'd like for us to do is to find out what the nodal force reactions are. So we're going to add something to our output. So here's our field output. Now there's field output and there's history output. Field output is something that changes spatially, like the stresses change spatially, so that's a field output parameter. Something that changes with time but not space would be our history output, like the total energy of the system. So I'm going to go in here into field output, and it's created in step 1. I'm going to double click on that. It's going to bring up this dialog, and right now it's what's called pre-selected defaults. So it's going to have displacements and different things, strains and whatnot. But let's see what I have here. So it has reaction forces and moments. But I want you to select this other thing called in-fork, nodal forces due to element stresses. I want you to select that. And we're also going to change the output. So right now it's going to output at for only 1 increment, so the first and last step. But we want to do an animation maybe where we have maybe 50. Okay, so let's do this at every in increments. Let's say 50 increments. We could change this to evenly spaced units of time if we want. Let's try this. If this doesn't work, I'll go back and change it. Alright, so I'm going to hit OK. And then let's create a job. I'm going to go down here, I'm going to left click, and then right click, create. We can call this job 1 if we want. That's kind of the default. A lot of times I'll have a lot of job 1s, and it's kind of hard to remember which one goes with which, so you may want to do something more descriptive. But this is coming from the source of the pipe without the seam. We're going to hit continue, and we're just going to take all the defaults in here. If you want double precision, you can change that, but I'll hit OK. Now, just because we created the job doesn't mean that we have submitted it. So I expanded this, going to select it, right click, and then hit submit. Now it says there's job files already. I already tried this once, just to make sure everything was working. So I'm going to go ahead and overwrite that. It's just kind of a caution. If you want to see what's going on, you can right click and monitor. And here's the increments. Okay, it said it's completed. We may need to go back and change the output if I don't get enough. But we're going to right click and select results, and then it'll bring up the results. You can also load in the results by going through file, but this is kind of convenient. Now this is just the undeformed model. If we click on this one, it says plot the stress contours on the deformed shape, then we see what this looks like. I'm going to hit this animation button, and it looks like it's only got the 2 steps. So let's redo this with more steps. I had a feeling that that wasn't quite right. So let's go back to our field output requests, and instead of saying every n increments, let's go let's see, every x units of time. If I do 0.02, I think that should give me 50 outputs. All right. So I'm going to come down here and right click again and resubmit this. Alright, so down at the bottom it says the analysis input file processor completed successfully. Okay, and here it is. It's just chugged through all of those increments, and we did get to 1 second. I'm going to dismiss this. It's completed, and I'm going to right click and click on results again. Well, that's a little unusual. I'm not sure what that error was. But let's see what this looks like now. Okay, so now we have 50 increments, and so it's kind of going slowly and increasing, and it's looping through this animation. That's on fast. If we want to slow it down, we can do that and hit apply. Now, what has shown up as the default stress unit is the stress for what's called the von Mises stress. We'll explain what the von Mises stress is in detail. But what we really want right now is the stress in the z direction. So I'm going to go up here to the top, and instead of this saying Mises, I'm going to go here, select S33 for the stress in the z direction. Now, since this load is ramping, these stresses are changing. If we want to get to the very last increment, what we'll do is we'll go up to the top and hit this kind of all the way over button, and that'll show the last increment. So kind of the interesting thing to look at is that we don't really have a uniform stress in this pipe, and the reason why is because of our boundary conditions. We have over-constrained this model. Alright, so back here you see how it's kind of this orangish color and this reddish color. Let's probe the values. We're going to go to Tools, Query, Node, Probe Values, change this to nodes, selected nodes, we'll maybe select this one. So that's got 1,066 pounds per square inch on the outside edge, and on the inside edge it has 930 pounds per square inch. Now if this is what you intended to model, this is what your stress distribution would look like. It's completely clamped on the right end, but free to contract away from that right end. Now this may not be what we want to do, so we're going to dig a little bit deeper and see if we can get a more uniform state of tension in this bar. Alright, so the way that we're going to do that, let's go back to my page here. Let's save this one just in case I need to come back to it. Alright, so I got a new page. Let's talk about what we would like to see happen instead of what we have. So right now I have this pipe and it's all fixed on this edge, and it's over constrained. Really what we would like to do is, if we're pulling on this pipe, we need to have it constrained in our Z direction, which is down the axis. But we want it to freely contract in the radial direction. So if I looked at the end view, we have our circle for the end view of our pipe. Maybe I can do a better job of a circle here. Okay, we want it to just draw in the radial direction. We're going to constrain it in the Z direction and in the theta direction. Oops. And we'll have no constraint in the radial direction. So we're going to do something a little bit more sophisticated now. We're going to set what's called a local coordinate system for our nodes. Okay. So let's take a look at that. Okay, so we're going back to our model here. I'm going to rotate it around so I can see the nodes. And I'm going to get in here and I'm going to, let's do this manager. So it's not clicking on the BC1, but it's clicking on the thing right above it. I'm going to right click and go to the manager. And here it says, it's created in the initial step. I'm just going to delete this. I'm going to get rid of that boundary condition. And now I'm going to right click and I'm going to create another one. We can call it BC1, you can call it something different. But it's going to be displacement and rotation condition. And it's going to be by angle, so we're going to select that bottom surface again. And now, instead of using the global coordinate system, I'm going to create a coordinate system. And I've done this a couple times, so that's why it says 4 on mine. But I'm going to create this system as a cylindrical system and hit continue. And it says select the point to be the origin. 0, 0, 0 is fine. So we're going to create that. And now it'll keep popping this up. So you have to hit cancel. But now if we constrain, we wanted to constrain, what do we say, the theta and the Z direction. That would be cylindrical coordinate system is r, theta, z, so that would be the 2 and the 3 directions, but we're going to choose, we're going to choose the coordinate system. And here it says we're going to select it, and here it's coordinate system 4, which is our cylindrical coordinate system. Then we're going to hit OK. Alright, now I'm going to create a new job, and we'll call it job 2 from pipe without seam. That's fine. And hit continue, and then we'll submit it. That's the only thing I changed, was changing the boundary conditions. And we should still have 50 increments, and it should continue on. Okay, so now we need to submit it. Files already exist because I've run a job 2 already sometime or another. I'm going to hit OK, and I'm just going to submit that job. It should go pretty quick. Now I do want to mention, at the first time you run ABAQUS, you may come up with like a Windows firewall thing that needs to work. Just let it through the firewall. It's fine. So it's running it. If we want, we can monitor it. It should just take a second or two, and it says it's completed successfully. Alright, now I'm going to go down here and right click on job 2 and look at the results for job 2. I'm going to look at the stresses. Now this shows the von Mises stress. Let's change it to S33. Get the axial stress, and I'm just going to right click, left click over here on the right double arrow to get to the last frame. And well, all of these are blue, but all of these numbers are 1,000 pounds per square inch. So I do have a very nice uniform stress field now. By relaxing that boundary condition a little bit, I can better simulate axial tension in this pipe. Now if I hit the animate, it'll just show you slowly the deformation increasing as the stresses change, because with time, between 0 and 1,000 pounds per square inch. Alright, so we're almost done. The last thing that we want to do is we want to calculate the displacement of the free end of the pipe and see if we get the right number. We can also calculate resultant forces. We'll try to do both of those things. But let's change this over here. Instead of stress, let's change this to U, which stands for displacement. And we'll go to the last frame in the analysis. Alright, so here the red looks like it's 1.206 times 10 to the minus 3. If we want to find out for sure where it is at the very end of it, we're going to query node values, and node, we're going to select the node on the edge, and yeah, it looks like 0.0, let me write this down, 0.0012 0599, and of course now that the unit would be in inches. Well, let's go back to our sketch pad and see if we can calculate what the displacement should have been for this pipe. So stress is related to strain through Hooke's law. If we have uniaxial tension, sigma is equal to E epsilon. We have, well, I guess we directly put in the stress. So we have sigma then is equal to epsilon, and the strain is, the engineering strain is the change in length divided by the initial length. So if we solve this for the change in length, that should be equal to the stress times the modulus of divided by the modulus of elasticity times the initial length. Now if we remember our numbers, we had 1,000 pounds per square inch. We're going to divide it by 30 million, and it was 36 inches long. Let me grab my calculator. So 1,000 divided by 30 million, it's 30 times 10 to the 6. going to multiply that by 36. And the number that I get from that is 1.2 times 10 to the minus 3. So let's see what we got again for our analysis. Okay, we got 0.0012, and then here we have 0.05999. All right, so it looks like it's off just a little bit, but it's pretty close to what we have. So we have the calculated value minus the accepted value over the, I guess let's do it over the accepted value. And we'll multiply that by 100 to get the percentage. And I got about 0.5%. Now that's pretty good. Now we may be able to improve upon that by doing some different things. Maybe we can use double precision or something like that. But for most engineering calculations, that is about as good as you're going to get for a finite element calculation as compared to all the other uncertainties that are involved in your calculations, such as the value of the modulus of elasticity and so on. Alright, so we did, I'm going to give you the mesh. You're going to import that. You're going to do what I've done. You're going to prepare your report. Then you're also going to do something else. Now, what I would suggest is maybe you can try different loadings. You can try maybe some different ways to do a boundary condition. Maybe you want to apply a load as a sine wave or a compressive load, just something like that. But I would like you to do, just think of something that you can do using the same mesh that I provide you. We'll keep it restricted just to the same mesh. But using my mesh that I'm going to give to you, do something else like we talked about in class, and then prepare your report. Alright, so I think that's good for this one.